So we start with the definition of the local extrema. Again, as I said, it's mirror what we learned in single variable calculus. The definition of a relative minimum, we're going to say that f of x, y. So for sake of discussion, I'm using a function of two variables, x and y, but this can be easily extended to a function of x, y, z, and so on. Matter of fact, it can be also downgraded to f of x by itself. So this is a generalized version of what we learned in Calculus 1. We're going to say that this function has a relative minimum at, since we're dealing with x, y, at the point a, b, if f of x, y is greater than or equal to f of a, b for all points inside a certain disk centered at a, b. Now this disk cannot be too big, so in single variable, the way we phrase it, we said near x equal a, all point f of x near x equal a. Here we're going to say inside the disk centered at AB in the vicinity of AB. So a little bit of a mouthful, but this is how we define relative minimum. Likewise, relative maximum, all we need to do is change the wording. F of x, y will be less than or equal to f of ab. So we'll write that f of x, y, again, the choice of two variables for sake of the example, is a relative maximum at AB if f of x, y is less than or equal to f of AB, making f of AB the maximum point for all points x, y inside a disk centered at AB in the vicinity of AB. So the third definition has to do with defining critical point, again mirroring Calculus 1. So we're going to say that the point AB is a critical point or stationary point and we'll talk about the term stationary point later on, not right now, of f of x, y, if one of the following is true. So what we expect to be true, let's mark it as 3. 3.1, and 3.2. The first one is that the gradient of of f at AB is the zero vector. Okay. In other words, this means that each component is zero. So we write here a note. Grad of AB equals 0 means that del x at AB equals 0 and del f del y at AB equals 0. In other words, both components. If one component is 0 and the other is not, then we cannot say that the gradient of f is 0. Again, the gradient is a vector, so the claim that the gradient is 0, meaning require that each component of the vector is 0. This is the case of two variables. If we have 3, of course, it will be, we need to include del f del z. If we have 4, we'll have to include del f del w, and so on. Okay, so that's one thing. The other, remember in single variable, the other case where we defined a critical point when the derivative is undefined, same here, we're going to say that either one or the other, so either component of the gradient vector, so either del f del x at AB does not exist, or, so the difference here is we have an or statement, del f del y at AB does not exist. And to complete this initial approach to minimum maximum, if you recall Fermat theorem in single variable, well, Fermat did not use the term critical point. This came later. Fermat talked about, he mentioned the derivative equals 0. If we do have a local extrema, a local minimum maximum, then in a single variable the derivative is a critical. We will have a local extrema at a critical point. Well, the same happen here. We're going to say that if a point, again I'm using the two variable set, if a point AB is a relative extrema, of f of xy, then AB is a critical point. It's a critical point of f of xy. In practice, and I should insert that here, for the sake of this course, a critical point will be the case where the gradient equals 0. So we won't have to deal with the condition of 3.2 for the time being, or for the duration of the course. So in this course, we'll have critical point such that the gradient is the 0 vector. Let's put only, so to eliminate the other possibility. All right.